Welcome back to the G-proof, rigorous mathematical proof that God exists, using first-order predicate logic and 5 axioms that no scientist can reasonably deny. This is video 2 out of 9 videos, and we have a website at thegproof.org. I'm Mark Lawrence Donald Emerson, and I'll be your teacher. So as I said, this is video 2. It's entitled Crash Course in Geometry Proofs. So here's a map of all 9 of our videos, which I showed you in video 1. And at the top right, I'm going to put a red box around it. There is video 1 up there. It's that cyan color, that light, bright blue color, because I'm assuming you've already watched it. We've been there. That color means been there, done that. All right, now I'm going to give you a fast tour of all the videos again right now. So on the left side of the slide, videos 2, 3, 4, and 5, that's where I'm teaching you the logic you need to know to understand our proof that God exists. Video 2 is, this is video 2 right here, which is why it's this pink color. This is a crash course in geometry proofs, and you're going to use those proofs on our journey to learning logic. And then in video 3, I'm going to teach you sentential logic. And then from there, in video 4, I'm going to teach you predicate logic, that's part A, and video 5 is part B of predicate logic. And predicate logic is what we need to prove that God exists. Then over in videos 6, 7, and 8, I'll teach you, this is on the right side of the slide, I'll teach you the proof that God exists. In video 7, we'll do our undefined terms and definitions, and the first 3 of our axioms, which I will justify. In video 7, we'll do the last 2 axioms and why they're justified, and talk about why the axioms are consistent, and I'll present an informal proof that God exists. And then in video 8, we'll do the formal, rigorous proof that God exists, the G-theorem. And then finally in video 9, we'll talk about the consequences of all this. All right, so here we are in video 2, and so let's talk for a minute about what the purposes of this video are. First of all, it is an educational step on the path to understanding our proof that God exists. You see, geometry proofs are the easiest way to learn about proofs. And I'm a very good geometry teacher. Whenever anyone is in my geometry class, 100% of the students in my geometry classes learn to do proofs within the first week of class starting from day 1. It always happens. A very good way of teaching it. I'm showing a part of that in these videos. I can't do the whole thing because it's a video. We don't have enough time. Now, although we're not going to use geometry proofs in our proof about God, we will use proof principles that are taught in this video. I'm not wasting your time here. This video, I'm showing you principles that we need. And then what's going to happen in video 3, we're going to switch to logic proofs. Logic proofs are harder all by themselves, but when you've had geometry proofs first and then feed into that, it makes it much smoother and easier to understand the logic proofs. Okay, another reason for this video is you might want to watch this video just to learn about geometry proofs. It could be a huge help to students taking geometry. Now, in this video, I will teach you 8 of the many rules of geometry. I will teach you how geometry proofs are structured and how they all fit together and why they make sense. I will not teach you in this video how to do your own proofs. This is a video, it's not a class. So here's an outline of this video. Let's go over the main bullet points. First one is points, segments, lines, angles, and triangles. The next bullet is the 8 rules that we're going to use. And the last one is we're going to do 2 example proofs in this video. Okay, so here we are on our map again. And you can see we're going to dive in and look and see those little symbols mean point, segment, angle, and triangle. We're going to do that now. Okay, so points, segments, angles, and triangles. All right, so here we are. Let's see what they mean. First of all, a point. What is a point? A point, I think you have an idea what a point is. A point is a very tiny thing. In fact, it's not just tiny, it's infinitely tiny. It has absolutely no size at all. What it does have is a location. It has a perfect location. It has a completely exact location, and that's all that it has. It has no size or anything. Now we can draw a dot, like up here I've got a couple of pink dots here to represent points. Now they're bigger than a real point. I have to give it some size so you can see it. So, but anyway, you understand the idea. The point, this represents a point and that represents a point. And in geometry what we're going to do is use capital letters to refer to points. This is point A, which I've written down here, and this is point C, which is right there, okay? Very easy. Now, line segments. First, let's talk about what a line is. A line is a straight thing. It's completely straight, and it goes infinitely far in both directions. Now, what we can do is, there's those points all along the line. If we take a point here on the line, and then another point down here on the line, and we clip the line off, then we have this piece of the line that goes from this point to this point. That's called a segment. All right? So these two pink things up here are segments. And what we do, the way we name the segment is we put two capital letters down. So see down here, this says AB. That represents this upper segment here. It's because it goes from the point A to the point B. And this one over here is obviously XY, or you could write it YX. It doesn't matter which order you put the two letters in. Triangles. Okay, what's a triangle? It has 3 sides and 3 angles, right? We take 3 points, and then we draw segments between the points, and that's a triangle. And how do we name a triangle? We write this little triangle sign followed by 3 capital letters. And what letters are they? They're the letters that are at the corners of the triangle, obviously. Here's triangle ABC on the left and triangle XYZ on the right. Very easy. And finally, angles. There's a lot more I could say about angles. I'm keeping it simple in this video. There's actually 3 different ways of naming angles. We're just going to use one way in this video, which is to put an angle sign with a number after it, like this. So what is an angle? Let's talk about that for a minute. If we take a whole line like this, and we take a point on that line, and then we chop off the part down here, so it goes from here infinitely far that way. Then we take another line like this, that also goes to the same point, and we chop off the part down there, so we have the part that goes up here infinitely far. So what goes up, these are like half lines, they're also called rays. So we have something like this. That's the angle. It goes infinitely, each direction. Now we can make the angle smaller or bigger, like this. Okay, so here we have a couple of angles, and we put a little number inside the angle like that. So this one is angle 3, and that one's angle 5. Very easy. Okay, now we're going to do 4 easy naming exercises. This is what my geometry students do on the first day of class. All right, so here's a diagram, and the question is, name the pink item. Oh, what is the pink item? It's a point. What's it called? It's called Q. Very easy. 1 letter for a point. Okay, name the pink item. What is this pink item? Well, it's a segment, right? And where does it get? It's from W to T. So what do we call it? WT, or we call it TW. Doesn't matter which way. Okay, very easy. What's this? Well, this one is obviously a triangle. What do we call it? We call it triangle PQV, or we can put the letters, when we name a triangle, we put the 3 letters in any order we want. Okay? Very easy. How about this? This is an angle, and in this video we're just naming angles by a single number. And what's the number that's in that angle? It's number 1, so we call it angle 1. Okay? So much for that. Now we're going to reverse this, and we're going to do 4 easy coloring exercises, which is the reverse of what we just did. Okay, here's another diagram. It says color C. So we have to put we have to color that on the diagram. What's it going to be? It's going to be a point. So C is a point right there. Very easy, right? What about this one? Color GD. Well, what's GD? That's a segment, right? Well, where's G and where's D? It's like this, just like that. See that? From G to D, right there. Very easy. Okay, triangle ABC. So we have to look for A, B, and C. If you look on the diagram, you can see A, B, C. Look carefully up there. And there's the triangle, right there. Very easy. Color angle 2. Where's angle 2? Well, the 2, you can see it right there. You can see the angle around it. So that angle is just like that. You see? Very easy. Okay, that takes care of our coloring exercises. Now we're going to do a tick exercise. All right, here's a diagram. Now what I'm going to do is I'm going to bring my little red pointer out here to help me out on this one. And what we have to do is put ticks on this diagram. We're going to do 4 of them here. Okay, the first one is, this is for equations. PQ equals ON. Now watch what we do. Where is PQ? PQ is right here. And where is ON? ON is over here. So what I'm going to do is I'm going to put a single tick on each of those like this. You see that? A single tick on each, and that means PQ equals ON. So you can look at the diagram and say, oh, I see, these 2 are equal. We're saying that by putting the ticks on it. All right, now let's do the next one. The next one down here says KL equals MN. All right, now where's KL? KL's up here. And where's M? MN is over here on the right. Now I already used single ticks. I need to go to double ticks now. And I do it like this. Okay, a double tick there, a double tick there. And KL equals MN. Very easy. Next one. Oh, now this was an angle. Angle 1 equals angle 2. Well, where is angle 1? Angle 1 is there. Angle 1 equals angle 3. Angle 1 is there, and angle 3 is up here. Now, what we do for angles is we put curved ticks like this. You see that? So angle 1 equals angle 3. We can see with the curved tick. One more. Angle 2 equals angle 4. Where's angle 2? Angle 2's there, and angle 4 is over there. Well, we already used single angle ticks, so now we go to a double angle tick like that. You see? That shows us that angle 2 is equal to angle 4. Now we can look at the diagram and see all those relationships from the tick marks. Okay? So that takes care of all that. We're done with this first part of the video. And so that's why I've made that cyan. And now we're ready to go on to the next part, which is geometry rules. Okay, so we're going to go through these rules now. Here's our outline. The first rule we're going to talk about is the definition of midpoint. All right, so here we have a segment, XY. What the midpoint does is the midpoint splits it into two equal parts. So if I make a statement, there it is, there's the midpoint right there. I'm just going to give it a name M. So I've got a red dot there. Now, if I have a statement that says M is the midpoint of XY. See, I made it pink there, that statement, quote unquote, M is the midpoint of XY. What does that mean? It means that XM is equal to MY, that the two pieces are equal. And so if I have that, what ticks do I put on the diagram? I don't put a red dot in the middle, I'm just doing that to show you here. The ticks I want to put on, if I have that something is a midpoint, I want to put ticks on for the two segments, and I do it like this. I put a single tick on XM and MY, or if I have to use double ticks, if I've already used single ticks up, doesn't matter. See that? Very easy. So M is the midpoint of XY, means I put ticks on like this for XM equals MY. Now, I'm going to show you a rule. This is the rule that, we will use it, this will appear when we're in the middle of doing proofs. And this says exactly what we just said. Here's a diagram, same diagram, and now it has two statements, that these two things in these pale yellow rectangles with curved sides on them, this one up here says M is the midpoint of XY. This one down here says XM equals MY. And what this rule says, if I have that, then I can say that. And see, the arrow is two-way. It also means if I have that, I can say that. If you don't understand what I mean by that yet, just hold on. Just bear with me, because when we get to the proof, you will understand it. Okay? Just introducing you to the rules now. All right, that takes care of rule number 1. Now let's go on to rule number 2, the definition of perpendicular. All right. Two lines are perpendicular. What does that mean? That means they meet at 90-degree angles. Not like this, but at a 90-degree angle. Okay, so here's a couple of lines and you can see, hopefully, they look like it's a 90-degree angle. So if I have this statement, here's how we write it. We say AB is perpendicular to XY using that upside down T, which is just trying to show that it's perpendicular. Okay, that's why that symbol is a good symbol. So this pink statement here says AB is perpendicular to XY. And what does that mean? It means that this angle 1 right here is equal to 90 degrees, right? Does that make sense? Now we have a special tick that we put on the diagram. Instead of using a curved tick for an angle, we use a square tick like this. That tick means that this angle equals 90. Okay? So now, here's how the rule will appear when we use in proofs. It says the very same, here's the very same diagram. And the statement up above here, this statement says AB is perpendicular to XY. And this statement down here says angle 1 equals 90 degrees. If I have this, I can get that. Also, if I have this, I can get that. We won't be going backwards on this rule in these videos. But it does work both ways. And now, the next rule is Rule 3, substitution of equals. So let's take a look at this rule. This is actually, we're going to do, in this video, we're going to do a simplified form of substitution of equals. When we get to video 4, we'll do the general form. Okay, substitution is actually not about geometry. It comes from logic. It's a special property of the equal sign itself. It's something that belongs to the equal sign, and like I said, we're going to use a special form of it. Now here's how it works. Supposing we know two things. The first thing we know is that A is equal to B. And the second thing we know is that A is equal to C. Well then what do we know? Then we know that B is equal to C, right? If A is equal to B and A is also equal to C, then B and C must be equal to each other, right? Very easy. And here it is how we're going to use it in the proofs. Now I'm going to use these colored dots. The reason I'm using these colored dots is that's going to be very important when we get to video 4. I want you to get used to it right now. I could have done it a different way, but this is real important in video 4. Okay, now what I have here, I have two things, you see, and two arrows. I have to have two statements already in order to use this. The first statement I have to have is that the red dot equals, the red thing equals the purple thing. See that? Red and purple. The next one says the red thing equals a blue thing. If I have the red equals a purple and I have the red equals the blue, then I can get that the blue is equal to the purple, right? It's the very same thing we said just a moment ago. Okay. All right, so that takes care of rule 3. And now before we do it, we're going to interrupt the rules for a minute to do another tick exercise. So here is tick exercise number 2. So I'm going to use my little red pointer again here. And our first one is angle 1 equals angle 3. Well, where's angle 1? It's here, and angle 3 is over here. So we're going to use a single angle tick for that, like this, okay? Our next one says angle 4 equals 90 degrees. Well, this is different because it doesn't say angle 4 equals some other angle. It says it equals 90. Well, where's angle 4? It's right here. So for 90 degrees, we use a special square tick like this. Okay? Very easy. Now the next one says E is the midpoint of DF. Well, what do we do about that? Where's DF? DF is here, and E, its midpoint E, is right here. Well, what does that mean? That means that these two pieces are equal. DE and EF are equal, which means we put ticks on for that, like this, to show those two are equal. Okay? And the next one down here is AD is perpendicular to DF. All right, where's AD? AD is here, and DF is here. And so what does it mean if they're perpendicular? It means they come together at a 90-degree angle, doesn't it? Well, where's the angle where they come together? That's right here at angle 2, isn't it? Well, what do we put on the diagram? We put in a square angle tick to show it's 90 degrees, like that, okay? And now lastly, down here, AC is equal to EF. Okay, now where's AC? AC is up here. And where's EF? E's over here. Oh, EF already has a tick on it. Already has a single tick. Well, what does that mean we're going to do? Well, if it has a single tick, then that means AC is equal to it. It can also get a single tick. So we just put a single tick on AC, which, by the way, is not only equal to EF, it's also equal to DE, right? So we can see all that on the picture now. All right, that takes care of our exercise, tick exercise number 2. So now let's go on to rule 4, the definition of congruent triangles. Before we get to the rule, I want to talk about what it means for two triangles to be congruent. It means that they are the same in every way except location. They're the same size, the same shape. The sides of one equal the sides of the other, and the angles of one equal the angles of the other, like this. Now let me show you. I have a little example here. Okay? So these two triangles, let's say this pink one is over here and this yellow one is over here. If they're congruent, then what it means is if we could move them, they would match up exactly. Well, I'd have to flip this one over and move this around like this, and you can see as I bring them together that they're going to match up like that. And then if I turn it over, you can see they match up exactly. That means they're congruent. Okay, although they weren't together. One's here, one's here. Okay? So, if we want to say that two triangles are congruent, we write it like this. We use a special symbol, which is an equal sign with a squiggle over it, which means is congruent to. So this statement says triangle ABC, which is the one on the top, is congruent to triangle DEF, the one on the bottom. Okay? Now let's talk about Rule 4, the definition of congruent triangles. All right, here are two triangles. Now, if we make a statement that says triangle ABC is congruent to triangle DEF, this means 6 things. The first 3 are these. It means AB equals DE, okay, that's one pair of sides, and BC, that's the single ticks, and BC equals EF, that's the double ticks, and AC equals DF, that's the triple ticks. See that? And the other 3 things are the angles. So angle A equals angle D, that's, well, that's actually the triple ticks, and angle B equals angle E, that's the single ticks, and angle C equals angle F. Okay? So now let's put this into our rule. This is the way we're going to see it on the proofs. Here's the same diagram with all those ticks on it. And if we know that the triangles are congruent, we have this statement up here, then we can have any of these. Once we know the triangles are congruent, we can have any pair of sides and any pair of angles, as long as they match up. Obviously, if we're using these two colored triangles here, we're not going to say that this short side here equals the long side over there on the pink one. Now it has to be this one here goes with this one, and this one goes with this one, etc. All right. So now we're going to go on to our next rule, rule number 5, which is called side, side, side. Now, how much is enough to make two triangles congruent? If we have 2 triangles here, but we don't know they're congruent, how much does it take to force them to be congruent? Now, if this was a geometry class, I would take quite a bit of time to go through this and show you how this works. I don't have time in these videos, so I'm just going to jump to what the answer is. There are 3 ways to do it. There are several ways to do it. We only need 2 in these videos. I'm just going to show them to you. In a class, we would take more time on this. All right? If I know that in one triangle, if I know that the sides are equal, in other words, I know that this side equals this one, and this side equals this one, and the long side equals the long one, then that forces them to be congruent. In other words, 3 pairs of equal sides forces the 2 triangles to be congruent. There's no wiggle room. You've got them nailed if you've got the 3 sides. Without knowing anything about the angles, if I know that the sides of this equal the sides of that, they are congruent. Okay? And that is called side, side, side. And here's how the rule looks. So now the diagram, now look on the diagram over here. It doesn't show any angle ticks. It just shows ticks for the 3 sides. Okay? Single, double, and triple. And what does the rule say? Now look at the rule. The rule has 3 arrows in it. And 3 boxes up here and 1 box down here. Okay, and what are those 3 boxes? Well, one of them is for the single tick sides, and one is for the double tick sides, and one is for the triple tick sides. You see that? RS equals XY, ST equals YZ, TR equals TZ. And each of those, we're going to call them stars. I'll explain what I mean by stars when we get into the proof. If I have all 3 of those, then what can I get? I can get that the triangles are congruent. And that's called side, side, side. All right, so that's rule number 5. Now, rule 6 is called side, angle, side. Now, this one is, what this one says is that if I have 2 pairs of sides equal, for instance, if I have these 2 sides equal, and I have these 2 long sides equal, then, without getting too confused here, so if I know this side equals this side, and this side equals this side, and I also know that this angle right here and this angle right here are equal, that will force the triangles to be congruent. That will also lock them up so there's no wiggle room. In other words, if I see how it's shown on the diagram here, I have the single tick sides, and I have the double tick sides, and the angle. The angle has to be between those 2. Can't be one of the other angles. So if I have 2 pairs of equal sides, plus 1 pair of equal angles between those sides, this forces the triangles to be congruent. This is called side, angle, side, right? Side, angle, side, like that. Okay? And so now, here's our rule. The diagram is a little different over here because you see there's no triple tick side. The 3rd side is missing, but we have an angle, and the angle is between the 2 sides. And again, we have 3 statements going in and 1 coming out. The 3 going in are what these ticks are, and they are also stars. So RS equals XY, that's the single ticks. Angle R equals angle X, which is the angle. And then TR equals XZ, which is the other side. So that gives us that the triangles are congruent by side, angle, side. All right, now we have two more rules to go. Rule 7. Rule 7 is called reflexivity of equals. And this is very simple. Anything equals itself. 25 is equal to 25. X is equal to X. Very simple. This is called reflexivity of equals. Now, we're going to use this in a special way in geometry proofs. Okay? If I have a diagram like this, we can use this to help get these two, see there's two triangles here. We can use this to help get them congruent because they share a side. Look at BD. BD in the middle, it's a side of the triangle on the right, and it's a side of the triangle on the left. It's a side of both triangles. And so what we can do, since it's a side on both triangles, we put a special tick on it to mean, oh, this is a shared side, and that's a circle. See, we're going to put a circle tick on it. See the circle tick we just put on there? That says, I am in both triangles. And what do we put in our proof from that? We're going to say, okay, well, that means BD is equal to BD. Well, BD equals BD anyway, always, but it's of significance here because it's shared between the two triangles. We'll use this when we get to a proof. And here is the way the rule will appear. There are no arrows on here. You don't have to know anything in advance to know that the red dot is equal to the red dot. It's automatic. It comes out of nowhere. And again, we're using dots because I'm going to use this rule also in the logic proofs later in video 4. Okay, now our last rule is called repetition. This is actually the easiest rule. All it says is that if we have something that's given, that we can repeat it inside the proof. It's very easy. We're also going to use this to repeat definitions and axioms in previously proved theorems. When we get to video 8, we'll do that. All right, here's the rule. If I have something, now this pink rounded rectangle here means a statement. And it means I can write the statement down again. I can just repeat it. Very simple rule. All right, so here are our 8 rules that we've just learned. I'm going to recite them quickly. We have definition of midpoint. We have definition of perpendicular. We have substitution of equals, although we're using a simplified version of substitution in this video. We'll use the general case in video 4 and 5 and in video 8. We have definition of congruent triangles. We have side, 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 side angle, side, reflexivity of equals, and repetition. Okay? Those are our rules. All right, so that takes care of our 8 geometry rules. I've made that cyan color on our diagram now. So now we move on to the last part of this video, which is our 2 example proofs. Okay? So, here we are, 2 example proofs. We're down at the bottom, but we have some work to do in each of these 2 proofs. All right, geometry proof number 1. Okay, before we do it, tips for doing geometry proofs. What we want to do in a geometry proof is we do it in 3 steps. I always teach students this way. The first step is ticks, and the second step is think, and the third step is write. I will explain what that means when we get into our first proof. Another tip is look for stars. If a line gets a star if it says a side of one triangle equals a side of another triangle, or if it says an angle of one triangle equals an angle of another triangle. Okay, that's what stars are. We're going to use these things. These tips are very important. We'll use them. Okay, here we go with proof number 1. All right, what we have is a diagram here. We have 3 givens, and we have something to prove. Okay, so let's begin with ticks. The first step is ticks. What we do is we're going to put ticks onto the diagram for each one of our givens. All right, so I'm going to bring my pointer out here, my red pointer again. All right, given number 1, what does it say? It says B is the midpoint of AC. Okay, I already taught you how to put ticks on. We're going to do it right now. All right, where's AC? AC's here. And where's B? It's right here. So it's the midpoint. What does that mean? It means the 2 pieces that the midpoint splits it into are equal. So we'll put ticks on for that, like this. Okay, single ticks. That takes care of given 1. Now let's move on to given number 2. It says BE is equal to DC. All right, well, BE is here, and DC is here. Well, I have to use double ticks now, right? So I'll put double ticks on for those. All right, now let's look at given number 3. It says that AB is equal to ED. Where's AB? AB is here. Oh, AB already has a single tick on it. And what about ED? It's up there. Well, Well, since AB already has a single tick, that means I get to put a single tick also on ED, like that, okay? Now I've got all my givens done. I put the ticks on for the givens. That takes care of step 1. Now step 2 is think. Well, when we think, we need to look and see, what are we trying to prove? We're trying to prove angle 1 equals angle 2. How are we going to do that? Well, first, where are they? Well, angle 1 is here, and angle 2 is here. How can we get angle 1 equal to angle 2? Well, I'm going to give you a big hint. What we need to do is we need to see if we can prove some triangles congruent. Do we have any triangles? As a matter of fact, we do. We have 2 triangles right here, next to each other. Now, if we could get those triangles congruent, would that help us to get angle 1 equal to angle 2? Well, as a matter of fact, angle 1 is in one of the triangles and angle 2 is in the other. So yeah, if the triangles are congruent, then we'll know they're equal. Now, what does it take to get 2 triangles congruent? So we're reasoning backwards here. And we go forward and backward in the thinking step. And when we do the proof, we only go forward. Okay, but right now we're figuring it out. It's like a puzzle. Okay? Well, if I'm going to get 2 triangles congruent, I need 3 stars. Because the 3 stars I'll use to get the triangles congruent. So, well, how many stars do we have? Let's look and see. All right, well, look at the double ticks. I got a double tick here on BE and another double tick on DC. Well, that's a star. Those are sides of these 2 triangles. What about the single ticks? Well, I got ED up here and I got BC down here. They're equal. That's also a star. But I don't have any other ticks. Well, AB doesn't help because it's out on the side. It's not in either one of the triangles. How can I get a 3rd star? Let's see, what could we do? Well, you know what? These 2 triangles are sharing a side, aren't they? Look at EC is in both of them. So that means that I can put a little circle tick on to show that they're shared. So I'll put a circle tick like that, and it's showing that EC is in the left triangle, and EC is in the right triangle. So that's also a star. All right, so now I've figured out what I'm going to do. So it's time to write the proof. When we write a proof, we use 4 columns. The columns are called line number, statement, from, and by. We're going to begin by using the rule of repetition, which says that if I have something already, I can copy it down. What I'm going to do is I'm going to copy given 1, which says B is the midpoint of AC. See that up there? And so I'm going to copy that right into here into line 1. B is the midpoint of AC. That's my statement. The line number is 1. The statement is B is the midpoint of AC. Where did that come from? Where did it come from? It came from up here, given 1. So I write given 1 in the from column. It says given 1. By what? By what rule? By the rule of repetition, which says that if I have something, I can copy it down again. And I have the givens. They were given to me. Okay? See how that happens? Now let's move on. Okay, we have now that B is the midpoint of AC. Is that a star? Well, no, because to be a star, it has to say something equals something. A star has to have an equal sign in it. This is not a star. I'm always going to be asking, is it a star? Is it a star? This is not a star. Well, I need to turn it into a star somehow. Well, in order to use this statement of this form, we need to use the definition of midpoint. So let's get that rule up here on the screen. Here's the definition of midpoint. And what it says is, if you have a statement of the form, something is a midpoint of something, then you can get an equation that says 2 things are equal. What 2 things? The things that are on either side. Here's the segment, here's the midpoint, the things that are on either side of the midpoint. So if we look at, if it says B is the midpoint of AC, up in our diagram, B is the midpoint. So that's why we put those 2 ticks on. Remember? These 2 ticks on A, B, and BC we put because we knew that B was the midpoint. That means by this rule we can get to this. So here's our second line. Number 2, AB equals BC. See that? AB equals BC. Now, where did that come from? It came from line 1. By what? By definition of midpoint. Now, look what. Let's analyze this. Definition of midpoint says I can go from a statement of this form to a statement of this form. What did I do? In line 1, I had a statement of this form that says the word midpoint in it. And in line 2, I have an equation with an equal sign that shows that the 2 sides are equal on either side of the midpoint. So I can go from here to here. That's what I did. I used the rule of definition of midpoint to get from line 1 to line 2. You see how that works? All right. Now, is this a star? AB equals BC. Well, it is an equation. The problem is that AB is not in either one of our triangles. It's out there on the side. So no, this is not a star. How are we going to get a star? Well, I'll tell you what. We're going to use the rule of repetition again, and we're going to bring in given number 3. So let's bring that in now. And so we get AB equals ED. Where did that come from? It came from given 3, which said AB equals ED, and by what? By repetition. I just repeated it in. Okay? Now what? Well, is this a star? AB equals ED. Well, ED is in one of the triangles. AB is not. It's still not a star because AB is not in either one of those triangles. How am I going to get a star? Well, I know that ED is equal to BC because they both have single ticks on them. What rule am I going to use? I need this rule. I need substitution of equals. What does it say? It says if the red equals the purple, if we have that, and if we also have the red equals the blue, then we can get that the blue equals the purple. Well, look what we have here in line 2. We have that AB equals BC. And then in line 3, we have that AB is equal to ED. Well, that means that BC and ED are equal to each other by this rule. See that? So that's going to be our line 4, that BC is equal to ED. And where did that come from? It came from lines 2 and 3. And by what? By substitution of equals. Now let's look again. You see these two things here, on the arrows go one way in this rule. These two statements here, the red equals the purple and the red equals the blue, those have to be things that you already had. Okay, we already had them in lines 2 and 3. So we're using line 2 and 3 by this rule to produce this thing down here, which is what our line 4 is. So you see how it's weaving together? What's happening is, what I'm teaching you in these videos is how proofs weave together. That's what I want you to see. Oh, and it weaves together by the rules. And all the things that go in the by column, everything in the by column on the right is a rule. And I will always use rules that you already have, that we've talked about. So far we've used repetition twice, we've used definition of midpoint, we used substitution of equals. And the from column in the middle is always going to be either a given or a previous line in the proof. And then when we get to video 8, it could also be definitions and axioms and previous theorems. Okay, so that takes care of line 4. Now, is line 4 a star? What does it say? BC, well that's in one of the triangles, equals ED, well that's in the other triangle. Yes, it gets a star. So I get to put a star. See, I'm putting a star right here in the margin. Right over there. Now we have a star. Okay. Now we need to get another star. Well, what are we going to do to get another star? I'll tell you what, we're going to use our repetition rule a third time. And we're going to bring in given number 2. So let's bring that in. That says BE equals BE equals DC, which is the double ticks on the diagram. Where is that from? It's from given 2, right? And how do we get it? By what? By repetition. Okay. Now, does this get a star? Well, it says BE equals DC. Those are the double ticks there. Yeah, one is in one triangle, the other's in the other triangle. It's a star. Okay, so we have another star here. That was an easy star. We need a third star. Where are we going to get it? We've used up the given. We got given 1 here in line 1, given 3 here in line 3, and given 2 in line 5. We've used up our givens. How are we going to get our third star? Well, remember what we did? What's that circle there? That circle we put on there because there's a side that's being shared. EC is in both of the triangles. But that means we're going to use our rule reflexivity of equals, which says that anything is equal to itself. The red dot is equal to the red dot. And so what can we say? We can say that EC is equal to EC. Where does that come from? It comes out of thin air. Anything is equal to itself. And by what? By reflexivity of equals. All right, now, is it a star? Now the fact that yes, it is a star because EC is in the left triangle, EC is also in the right triangle. Okay? And so that makes this a star. Hey, now we have 3 stars. If we have 3 stars, that means we can get the triangles congruent. And this is the rule we need. We don't have any angles here, just sides. We've got side, side, side. You see that? We've got the single tick side, the double tick side, and the circle, which is a shared side in the middle. All right, now what we have to have is we have to have 3 separate lines, which are stars, which are sides. And that's what we have. Look at lines 4, 5, and 6. We've got those 3 things, which means that we can get that the triangles are congruent. So that's what I'm going to write now. In line 7, I can say triangle BEC up here, the one on the left, is congruent to triangle DCE, which is the one on the right. Where did that come from? It came from the 3 stars, lines 4, 5, and 6. See? 4, 5, and 6. Those are the lines with the stars that gave us exactly what we required. This rule requires 3 stars. If you have the 3 stars, then you get the triangles are congruent. So it came from lines 4, 5, and 6 by what? By this rule right here, side, side, side. Okay? I have the SSS in parentheses because we can use the abbreviations. We'll do that a lot when we get to logic because the bicolumn is going to get much narrower. Okay, now we have the triangles congruent. Well, better back. What was our strategy after that? Well, once we had the triangle congruent, well, look what we're trying to prove. We're trying to prove that angle 1 equals angle 2. We just about got it. We need one more rule. We need this rule here, the definition of congruent triangles. What it says is if we already know the triangles are congruent, then we can have any of the pieces that we want to be equal as long as they match up properly. Okay? And so what do we have? We have right here in line 7, we have that the triangles are congruent. So, and angle 1 and angle 2 are in one is in one triangle, the other is in the other, so we can make them equal now. So we can get line 8, angle 1 equals angle 2. Now where did that come from? It came from line 7. By what? By this rule here, definition of congruent triangles. You see that? And so this requires one statement that the triangles are congruent, and then we only needed one of them. There's 6 options here. We only needed one of them, which was the angle 1 equals angle 2. And so now, we now have angle 1 equals angle 2 in our proof. That means we're done. We proved it. We just proved that angle 1 is equal to angle 2 based on these 3 givens. Now, what I want you to see is how that all weaves together. We brought the givens in, we used the rules, we used one. Look how the lines are, they wove together, and everything we needed, it's all there, and it ended up proving what we wanted to prove. Now, if you don't get it, if you don't see it yet, or you didn't quite get it, please back up the video and watch me do this proof again. Sometimes you need to see it more than once to get it in. If you just watch it once, maybe twice more, you will get it and you'll see, oh, it's so beautiful. It just fits together. It's like, yeah, it all makes sense. And that's the idea. Okay? So now, let's go on to proof number 2. All right, here it is. This is a little more complicated. We've got a diagram over here, a little more complicated. We have 5 givens this time, and we have something to prove. So I'm going to bring my little pointer out again, and let's do our first step, was to put the ticks on for the givens, right? Ticks, then think, then write. Okay, let's start with given 1. Given 1 says that VT is perpendicular to WT. Well, where are those? Well, VT is here, and WT is here. What does it mean that they're perpendicular? It means that they form a right angle. It means they form 90-degree angle. Where's the angle? Well, the angle is 2, right? It's angle 2. That means we're going to put a square angle tick on for angle 2. And now, the next one, W is the midpoint of RT. Let's see, where is RT? RT is right here, and W is right there. W is the midpoint. That means it splits it into 2 equal pieces. And so we're going to use ticks for that and put them on there. RW and WT are equal because it's the midpoint, okay? And the next given, given 3, says ST equals WV. Well, okay, ST equals WV. I already put the ticks on too soon here. Anyway, so we're going to put ticks there, a double tick there for ST, and a double tick on WV. I pushed my button too soon. That's okay. You can see what's going on. All right, and then given 4, angle 1 equals 90. Angle 1 is up here, 90 degrees. So I put a square tick on angle 1, like that. And then finally, given 5, RW is equal to UV. Well, RW is over here. Oh, RW already has a single tick on it. And it equals UV. That means UV can also get a single tick, right? So we'll put that up there like that. And now we have all of our givens. The next step is to think. Well, we have to prove here, we have to prove T is the midpoint of SU. Okay, here's T, and here's SU, right there. In order to do that, we would have to show that the two pieces are equal, right? We'd have to prove that TU and ST are equal. Well, I've got a double tick on ST, but I don't have any ticks on TU. I can't, it's not okay to go putting a double tick on there now. That's what we're trying to prove. Okay, we put ticks on from the givens, but not from the proof. Okay, so how are we going to get those equal? Well, I tell you what, maybe we could find a couple of triangles that are congruent. Do we have any triangles? Yeah, we actually have 3. We have these 2 smaller ones up here, and we have this big one down here. Well, this big one down here it's obviously not congruent to any of the others, but these 2 little ones up here, they might be congruent to each other. What if they were congruent? Well, if they were congruent, then WV over here with the double tick would equal TU, wouldn't it? Now, if WV equals TU, and then at that point, if I finally proved that, then I could put a double tick on TU. Can't yet, because I don't know yet. And that would mean that ST and TU are equal to each other. And that would force T to be the midpoint, wouldn't it? That's how we could get it. But remember, we would have to get the triangles congruent. The 2 top triangles, the little ones. Well, how are we going to get the 2 triangles congruent? Well, remember, to get triangles congruent, we need 3 stars. How many stars do we have? Well, let's see. Look at the singles ticks. We have VU and WT. Those are side of one triangle, a side of the other triangle. That's a star. Then we have a double tick over here on WV, but that's not a star. ST down here is not in one of those 2 little triangles. And we don't have any tick on TU. In fact, that's what we're trying to get. We're trying to get that. So that's not going to be a star. WV is not going to help to get the triangles congruent. We'll use it later, after we've got them congruent. Well, let's see. We've got 1 star so far. Oh, look at these 2 angles, angle 1 and angle 2. Well, they're both 90 degrees. They must be equal to each other, right? So angle 1 and angle 2 must be equal. That's a star. Let's see. What else have we got? Oh, look at VT. These 2 triangles are sharing a side. VT is in both of the little triangles, isn't it? So let's go ahead and put a circle tick on there like that to show that these 2 triangles are, the 2 triangles share this side. It's in both of them. All right, well, that's our 3rd star. Now, what are we going to, we have side, 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 angle, side. Let's look. Actually, so we're using the angle here, angle 1 and angle 2. Let's see if it works for side, angle, side. Okay, let's look at the triangle on the left. We have a side here with a single tick. We have an angle here with the 2, and we have a side here with the circle. So that's side, angle, side. Now let's look at the other triangle on the right. We have VU here, that's a side. We have angle 1, that's an angle. And we have a circle here, which is another side. That's also side, angle, side. It will work. So that's how we'll do it. We'll have 3 stars. We'll get our triangles congruent. Then we'll set that WV equals TU, and then we can put our double tick on TU finally when we get way down there. And then we can get the midpoint. Okay? So now, let's go ahead and write the proof. So we're going to use 4 columns, line number, which is just numbers, 1, 2, 3, 4, all the way as far as it needs to go. Statement. The statements are where we're stating the things that we're proving as we go. The from column lists previous line numbers from the line number column, from higher up lines, also lists givens. And the by column lists rules. Everything in the by column is one of the rules, and we have 8 rules that we're dealing with in this video too. All right, so let's begin by bringing in given number 1. And by the way, I'm not going to put that repetition rule down there anymore. It's so simple. I'll just leave it out. I'm just going to go ahead and write given 1 down here, which says that Vt is perpendicular to Wt. Where does that come from? From given 1 by the rule of repetition. Okay. Now, does this get a star? It has a perpendicular sign in it. A star has to say something in this triangle equals something in that triangle, so no, it doesn't get a star. Well, how can I get a star from it? What can I do with it? Well, I need the definition of perpendicular. I need this rule here, which says that if I know that two things are perpendicular to each other, then I can get some angle is equal to 90. It has to be the angle where they meet, which in this diagram is angle 1, but it's not angle 1 in our diagram. We have Vt is perpendicular to Wt. You can see, if you remember, okay, they meet at angle 2. Angle 2, that's why we put the square tick on angle 2, because we had one from given 1, okay? For the Vt is perpendicular to Wt. So that's what we can say now by this rule. We can say in line 2, we can say angle 2 equals 90. From where? From line 1. By what rule? This one right here. Definition of perpendicular. See that? All right, now, is this a star? It says angle 2 equals 90. Well, angle 2 is in one of the triangles, but 90 isn't. There's nothing from the other triangle, so no, it doesn't get a star. So how can we make this into a star? Well, we need to use given 4. Let's bring given 4 in, which says angle 1 equals 90. Where's that from? Well, given 4 by repetition. Okay. Is this a star? Once again, no, because although angle 1 is in one of the triangles, 90 isn't. But what can we do now to get a star? Look at lines 2 and 3. We have angle 2 is equal to 90, and we also have angle 1 is equal to 90. Well, that means we can use this rule here, substitution. If the red equals the purple, and the red equals the blue, then the blue equals the purple, right? Now, I realize they're turned around the other way because the 90s are on the right. Doesn't matter. Equations can go either way. So that means that angle 1 equals angle 2, right? So I can say angle 1 equals angle 2, and where did that come from? It came from lines 2 and 3, which is why I wrote 2 and 3 in the from column. By what rule? This one. Now I want to tell you a little bit more about these rules. These rules have arrows in them. Look at the arrows in this rule. It has 2 arrows. That means that we have to have 2 entries in the from column when we use this rule, because we have to have two prior lines, one like this and one like this, to produce this. And that's what we have here. We have 2 things in the from column, 2 and 3, which are the 2 lines. 2 and 3 are the 2 lines that are like these 2 lines. See how that fits together? All right, now is this a star? Well, angle 1 is in the little triangle on the right, and angle 2 is in the little triangle on the left. So yes, it's a star. Let's put our star in. Okay, we got a star. Now we need 2 more stars, right? All right, let's go for given number 2. Let's bring that in. So that says W is the midpoint of RT. Where is it from? Given 2 by repetition. Is this a star? It says something is a midpoint. The word midpoint isn't going to be a star. A star has to have an equal sign in it. So how are we going to use this? We need a rule. And the rule is definition of midpoint, which lets us move from a statement with the word midpoint in it, to another statement that has an equal sign that says 2 things are equal, which are the 2 pieces on either side of the midpoint that the midpoint splits the segment into. All right? Well, what do we have up here? We have W is the midpoint of RT. Okay, up here in our diagram, W is the midpoint of RT. Look, that's why we put those 2 single ticks in there, one on either side of W. So that means that's what we can say. We can say RW equals WT. Let's put that down now as our next line. RW equals WT. Where did that come from? It came from line 5 by what? Definition of midpoint. Now, definition of midpoint has a double arrow in it. We're only using the arrow in the downward direction now. And not only that, it's just one arrow, meaning the downward arrow. So that means we only have to have one thing in the from column, and we have just one item, number 5. This rule, since it has a double arrow, we could also use it in reverse, and we're going to use it in reverse at the end of this proof. We'll bring it back. Okay. Now, is this a star? RW equals WT. Well, I got a problem with RW. RW is out on the side. It's hanging out there on the side. It is not in either one of the little triangles, so no, this is not a star, even though it does have an equal sign. How are we going to get a star from this? Well, we need another given. We need given 5. Let's bring given 5 in, which says RW equals WV. Where's that from? Given 5 by repetition, right? Look at WV up here. That's why we put the single tick up on WV, remember? Because WV is equal to RW. I didn't say that right. VU, as up here at the top, is equal to RW. And so, now is this a star? Well, it still has the RW in it because RW is out on the side, so no, it doesn't get a star, but look at lines 6 and 7. 6 and 7, RW equals WT. RW also equals VU, so we can use our rule of substitution again. Okay, red equals purple, red equals blue. We have those two things, then we can get that blue equals the purple. 2 arrows, we need 2 items in the from column. So here we go. We can say UV equals WT. Where's that from? 6 and 7 by substitution of equals. All right. Is this a star? Well, UV is in the triangle on the right, the little one, the little triangle on the right, and WT is in the little triangle on the left, so yes, it gets a star. So let's put our star on there. Now we have 2 stars. Now where are we going to get our 3rd star? Well, if you remember, we have a circle up here. Why do we put the circle there? Because VT is shared by both of the 2 little triangles. So we're going to use this rule here. Reflexivity of equals says anything is equal to itself. And so that means we can say that VT is equal to VT. Where's that from? Comes out of thin air. Anything is equal to itself. By what rule? Reflexivity of equals. Now let me tell you something. Look at this rule. This rule has no arrows. It has no arrows, but you don't need to know anything in advance to know that something equals itself. And since it has no arrows, it doesn't require any items in the from column, which is why there's a dash in the from column. You don't need anything, because there's no arrow in the rule. So the number of arrows in the rule that you're using determines how many items must be listed in the from column. Okay? Now, is this a star? Well, VT is shared by both triangles. It's in one triangle and it's in the other triangle, so yes, it gets a star. Now let me point something out here. This reflexivity of equals could be used to do anything. I mean, look at RS. RS is hanging out there over on the boonies, over on the side there, at the bottom left. RS is not in either one of those 2 triangles. I could say RS equals RS by reflexivity of equals. It absolutely does. The problem is, it wouldn't be a star. It would be a waste. It would be useless. We needed a star here. So the reflexivity of equals is useful to get stars. Well, now look, we have 3 stars. Well, we need 3 stars to get our triangles congruent, and how are we going to do that? Remember, we looked at it, we decided we have an angle and 2 sides, and the angle is between the 2 sides. We already walked through that when we were doing our thinking step. So we're going to use our side angle side rule, which says that if I have 2 sides, 2 pairs of sides equal, and 1 pair of angles equal, then I get the triangles are congruent. And this rule has 3 arrows. Because it has 3 arrows, that means I have to list 3 items in the from column. And what items are those? The stars. Okay, so we've got it already set up here. We can see clearly, oh, these are the 3 with the star. Those are the 3 items that are going to go in the from column to correspond with the 3 arrows in this rule here. See that? And what are they? We need a pair of sides equal, a pair of angles equal, a pair of sides equal. Well, we've got the pair of angles listed first in line 4, and then a pair of sides in line 8, and a pair of sides in line 9. It doesn't matter that we did the angles first. All that matters is that we have all 3 of these before line 10. So now we can write in line 10, we can say that the triangles are congruent. Triangle VUT, that's a little triangle on the right, and triangle TWV, which is a little triangle on the left. From what? The stars from lines 4, 8, and 9. By what rule? This one. Side, angle, side. Okay? Alright, now that we've got the triangles congruent, we have to revert to why did we even bother to do that? Remember, we're trying to prove that T is the midpoint of SU. Well, how are we going to do that? We needed to prove that TS is equal to TU, right? To show that it's the midpoint. And we have a double tick on TS, because it's equal to WV, what we wanted to get is a double tick on TU. Well, now that we know the 2 little triangles are congruent, that means that WV, which has a double tick, is equal to TU. See that? So that means we need to get those equal. We need to get WV is, well, we can state that WV is equal to TU now. We can say it, and how could we say it? Since the triangles are congruent, we need to use this rule here, which is the definition of congruent triangle, which says if I know two triangles are congruent, then I can have any of the pieces equal, any of the sides, any of the angles, as long as they match up. All right? And which ones do I want? I want WV and TU. So that's what I'm going to say now. I'm going to say TU, I said it the other way, TU is equal to WV. And where does that come from? That comes from line 10, by definition of congruent triangles. By the way, I've written it with the abbreviation because I don't have room, so I put the congruent sign, a little triangle sign, and an S, okay, just so it'll fit. All right. So, and by the way, this rule has one arrow. Now it's a double arrow, it goes both ways. We never use it in the up direction. And the down direction, that means we need one item in the from column, and we have it. Here it is, number 10. And number 10 is the thing that says that two triangles are congruent, which is exactly what this is here. Okay? See how it fits all together. All right. And now what? Well, now that I've got TU is equal to WV, I can finally put my double tick on. I've proved it now. When I was doing my thinking stuff, I hadn't proved it yet. Now that I've proved it, I'm going to go ahead and put that double tick up there on TU right now, just like that, okay? But what I really want is that TU is equal to ST. We can see from the ticks there, but how do we get that into the proof? Well, you know what? We need given 3. Let's bring given 3 in now. Given 3, ST, that's at the bottom here, equals WV. That's from given 3 by repetition. And now, look at lines 11 and 12. We have TU is equal to WV, and ST is also equal to WV. We need to use substitution again. I'm going to put the substitution rule up here. I don't have room at the bottom, so I'm covering some of this up and get it out of the way in a moment. Okay? So we can use lines 11 and 12 to say that that ST is equal to TU. You see that? From lines 11 and 12 by substitution of equals. This rule requires 2 lines, two items in the from column because there are 2 arrows. Okay. Well, now we're very close. ST equals TU. Look at that. We're trying to prove that T is the midpoint. Well, we need to get the word midpoint back in again, although this is a different midpoint. We need the midpoint rule, which is definition of midpoint. And this time we're going to go up. Because a double arrow, we can go either way. Now we need to go the other way because we have the equation. We want to get the word midpoint. Okay? And so that's what we can do. We can now say, because we have that these two pieces are equal, the ST and TU. So now we can say that T is the midpoint of SU. And that's what I'm going to put here. T is the midpoint of SU. Where did that come from? Line 13 by definition of midpoint, going up in the reverse direction. By the way, definitions are always two-way. Okay, and there it is. Now we've proven it. The proof is complete. Now I have a comment to make. The way that this, first of all, if you didn't understand it, if you got lost, if you got confused at some point, please back the video up and watch me do it again. And then you will get it. Maybe you need to watch it a couple more times. It all fits together beautifully. You can get it. Just watch it and see how it all fits together. What I want you to understand is that we have 4 columns and that we use our givens and we use rules and we make one statement and then we make another statement, and each time we make a statement we're getting it from other stuff. And they're all weaving together. The from column is showing how things are connected to what, and the by column is showing what rules we're using to connect them together. And all of that we are going to do when we do logic proofs. We're just going to do it without diagrams. Okay, so we're done. We're done with video 2. We have completed our crash course. That's why I have made this video 2 cyan color. And now, just as a quick note, the historic leap we talked about in video 1, that's what happens here. When we move now to sentential logic and predicate logic. This is what happened after 1879. Talked about that before. And so the next video will be video 3, when we will take what we just learned about weaving things together, we'll drop the diagram, we'll drop the geometry rules, and I'm going to show you new rules that we're going to use in logic. Okay, so thank you very much for watching. I'm Mark Lawrence Donald Emerson.